Hi, this is Ms. Wensloff. Today I'm going to be taking you through lots of different situations with forces in two dimensions. During this flip lesson, I encourage you to pause, rewind, stop, take a break, and also come back to it in the future. Let's get started. So far we've talked a lot about forces. And one of the things we've been focusing on is direction, which makes forces a vector. So this is one of the most important things here, that they are vectors, which means they have a direction. Now, so far we've really only been working in one dimension, or if we had two dimensions, everything was in a nice straight line. So if I have a force off to an angle, the same thing as I did before, I'm going to have to break it up into its x and its y components. Okay, since forces are vectors, I need to break them up into x and y. So as we go through parts of this chapter, it's really important to think, if I have a force at an angle, I need to break it up into its x and y components. All right, so let's look at one of our first situations where we're really focusing on the vectors of forces. Now, if objects are at an equilibrium, like in this picture over here, that means the object is at rest and the sum of forces is 0. Now, if I look at this image, we can see that I have forces in the x and the y direction, and I also have T1 that's at an angle, okay? Now, in these problems, I'm looking for T1 and T2. That's the tension on the ropes. Now, before I get started with anything else, the first thing I need to do is break up this 30 degrees into its x and its y components. You'll notice that I draw which way the arrows is going, because that's going to help me a little bit later. Now, what is this going to look like? For my x, I'm going to have T1 sine 30 degrees, y its opposite, and then I'm going to have T1 cosine 30 degrees, y its adjacent. Sorry, that's a little bit messy. Now, at this point, I have everything broken up into x and y, so I can make my x and y chart. Let's start with the mass that's hanging down. We're going to assume that I have a pretty standard system for my directions. Okay, so I have my mass hanging down, so that would be a negative 150 newtons. Why is it negative? That's down. And then T2 is going to the positive in the x. Now I have that T1 that's broken up in x and y. In the x direction, I have negative T1 sine 30 degrees, and in the y, I have positive T1 cosine 30 degrees. Now, this object is at rest, which is really important to us. So I'm going to solve for T1 and T2 using the fact that all of these are equal to 0. Okay, this is really going to help me. Okay, so in my y direction, I have all my forces, my sum of forces in y is equal to 0. Here I have T1 cosine 30 degrees minus 150, and that's going to give me 0. I'm solving for T1, so I'm going to bring that 150 over to the other side. And then I'm going to divide by cosine 30. This is going to give me that my first tension is 173.2 newtons. Now, I also have my x direction. If I set up my x direction, let me change colors. My forces in the x are also equal to 0. And I have T2 minus T1 sine 30 degrees equals 0. Now, I'm solving for T2, and I already know what my T1 is. So I'm going to have T2 equals T1 sine 30 degrees. Just rearrange my equation there. And then I'm going to plug in my T1 that I found above. So this is going to give me for T2 equal to 86.6 newtons. So really my setup is important in these problems. After that, it's really just using math and using my algebra skills to get there. All right. Now, our next situation we're going to have is when I have objects at a vector, except they're moving, okay? So this is going to be set up kind of similar to the problem we just did, except that we have this object's actually moving. So let's say that we are pulling this sled, which is 35 kilograms, and we're pulling at an angle of 30 degrees, and it's moving horizontally. And by moving, it is accelerating horizontally. Now, this is going to be pretty important to us. If I look at this triangle more in depth, I have 60 newtons, and then I have 30 degrees here. So the first thing I always want to do in these problems is break up my x and y components. So I have 60 cosine 30, it's adjacent, and then I have 60 sine 30, and that is opposite. Okay, now this is accelerating only in the x, so I actually only care about what's happening in the x direction. So I really don't even have to worry about this y direction. Why? Because the forces are balancing out, it's not moving in that direction. Now, because it's moving, this is when I use Newton's second law, which, remember, this is written a little bit differently. We have all my forces in the x over m. The only force I have in the x is that 60 cosine 30 degrees over my mass, which is 35 kilograms. So if I do my math for this, I'm going to get an acceleration of 1.48 meters per second. Okay. At this point, I could start solving for additional motion parts, like how far does it travel in 3 seconds or something like that. Now, one last thing I want to emphasize before I move on is that we need to focus on what direction this thing is moving. That is going to dictate what parts of that vector I'm going to use. Okay, our next topic we're going to talk about is friction. So, we have two different types of friction. We have static and kinetic friction. So friction, we typically see that something's slowing down, it's inhibiting some type of movement. So for static friction, this is the friction that's opposite to prevent that motion. So if we think about when we're pushing a heavy box, it takes us a little bit of time to get it started. Once we get started though, it's a lot easier. Now for static friction, this is the friction that holds it in place. Kinetic is the friction that's actually there when it's moving. We can see in this free body diagram for static, everything's equal, but in kinetic, we have a lot more push. Now, if we compare these two, I think this is really interesting. My static friction and push are equal, but for kinetic, my kinetic is less than the push. That makes sense because it's actually moving. So my equation for friction is going to be pretty important to us, and I would take a moment right now to find that on your AP Physics 1 equation sheet. This is saying our force of friction, and this could be static or kinetic friction, is equal to the coefficient of static friction. So this is a number between 0 and 1. It's really just a proportion. And that is times n, which is my normal force. Now, we've been talking a lot about weight, but normal force is related to weight. Not always is it equal, though. So this is going to be really important to us as we get into these situations. All right, so let's get started on our inclined planes. So inclined planes are where we really start applying all the friction and our knowledge about forces. Now, if I look at this inclined plane, let's say I have a block on it, and let's say that I have an angle of 30 degrees. Let's kind of like keep that my constant angle during this. Now, let's say that my box is sitting on this inclined plane, and it is at rest. So if it's at rest, that means we know that all of my forces on all sides are equal to each other. Now, before we get started, let's write down all the forces that are acting on this object. So first, we have our force of gravity, which is equal to mass times gravity. That's going straight down. Now, if we think about what we learned previously, my normal force is always perpendicular to the object. So that means my force normal is actually at this angle. It's kind of weird. And then I also have my force of friction, which is keeping this back. Okay? Now, this is kind of interesting. If we really study this image, you'll notice that, well, everything's at an angle except for my force of gravity. So when we set up our when we set up our coordinate system, we need to keep that in mind. So when I set my coordinate system, actually, it's at an angle, okay? This is the coordinate system I personally like to use for this. So I have going down as positive because that's kind of what we would think of would be positive. It's going to kind of help us out later on. Now, because my orientation is at an angle, that means I need to break up my force of gravity into x and y components. How am I going to do that? It's going to look something like this. Now, because of alternate interior angles, this also means that this is also 30 degrees. This is telling me that this mg, my force of gravity, is my hypotenuse. So if I want to figure out this first component, my y component, okay, so I'm going to reiterate where it was because I just got interrupted. So my FG is my hypotenuse. So now I'm going to look for this y component, and this is going to be FG, my force of gravity, cosine 30 degrees. And on the other side, I'm going to have FG sine 30 degrees. Why? It's opposite. Okay? This is super important. My x component is down here, and my y component is over here. Okay? Now, I have to break up this force of gravity. Think about for a second to yourself why. Because my coordinate plane is also at an angle. All right, so let's make my x and y chart here. Okay, so on my x and y chart, in the x direction, in the positive, I have that mg sine 30. I'm going to need a little bit more room, so let me rewrite this. So I'm going to have, there we go, in the x, in the positive direction, because of how I did my forces, I'm going to have mg sine 30. Okay? And then in the opposite direction, negative, I have my force of friction. Okay? In my y direction, in the positive, I have my force normal. And in my negative, I have my mg cosine 30. Now, at this point, I can actually start solving for what I want to. So in this particular problem, I could solve for a lot of different things. Typically, we're solving for our force of friction or our coefficient of friction. This is going to be coefficient of static friction. So I'm going to be looking for mu s in this problem. Okay, so let's continue solving. In my x direction, I have mg sine theta minus my force of friction equals 0. Okay, so I can set these two things equal to each other because it's 0. Think to yourself, why is it 0? Well, it's 0 because it is at rest. Okay, now what I can do is I can substitute in my equation for force of friction. So I'm going to get mg sine 30 degrees equals mu force normal. Divide both sides by force normal. So my equation is going to be mu equals mg sine 30 degrees over force normal. Now I actually don't know force normal yet, so let's go to the y direction and let's solve. So in my y direction, I'll label this y and x. There we go. In my y direction, I have force normal minus mg cosine theta equals 0. So if I solve for force normal, I'm going to get mg cosine theta. So this is really interesting. My force normal is not actually equal to gravity. It's equal to a component of gravity. This is huge for us. Let's substitute this in. So now I have my mu, that's mg sine theta. I'm going to substitute in my force normal, which is mg cosine theta. This is so cool. Look what goes away. My g's cancel, and also my mass cancel. You may notice at the beginning of this, I never gave you what the mass was, because it's actually not significant. So for my coefficient of static friction, I'm going to get 0.577. Now, this does make sense because this is a proportion. It is always between 0 and 1. So take a deep breath, look at what we just learned. We're going to move on to a different situation. Okay, so the next situation that we may have is that this block is accelerating with no friction, okay? So if we think about this, that means it is accelerating downward, okay? And remember, because this is at an angle, we are going to keep this same exact orientation, okay? It's going to be at its side. So if I draw my free body diagram, I'm going to have my force normal, my force gravity, and then that's about it. I have no friction in this situation, so there's nothing else going on. So I'm going to do the same thing. I'm going to split up my gravity into its x and y components. So that's going to be mg cosine theta, or 30 degrees. This sign's going to be mg sine 30 degrees. Now, this is super important. My x is the only one that's moving. My y direction, though, is staying equal. That means that the only part of this that I care about is my x direction, because that's the only way that it is moving, in the x direction. So if we look at my forces, the only force I have in my x is that mg sine theta, okay? So this is the only thing that's pushing this thing down the ramp. Because it's moving, I'm going to use my sum of forces over m is equal to a. And let's solve for the acceleration. So my only force I have is mg sine theta over m equals a. Once again, didn't give you mass because I don't need it. I can get rid of that. So if I plug in my numbers, all I'm doing is 9.8 sine 30 degrees. And that's going to give me acceleration of 4.9 meters per second squared. So this is really interesting. My gravity is the only thing that is pulling this down the ramp. If there's no friction, it's the only thing that's pulling it down the ramp. So my next example, I'm going to combine something accelerating down a ramp and add friction onto it. We're going to combine these two things that we just learned. Okay, so in this situation, we're going to say that something's accelerating with friction. So let's set up our free body diagram like I did before. I have force normal. I have force of friction going the opposite way of motion. Always the opposite way of motion. And then I have my force gravity. And once again, I need to break it up in the x and y components. Now, before I take some time to actually break that up, what is the only way it's moving in? It is only moving in the x direction, keeping the same exact compass that I did before, okay? Which means the only thing I really care about is this x component of gravity. So remember, that's going to be mg sine theta. And let's keep this at 30 degrees. Sorry, I didn't say that before, okay? So let's actually break this down and solve to figure out what's going on. Okay, so in my x and y components, in my x, I have negative force of friction, that's opposite, and then I have mg sine theta. And remember, my x direction, all my forces equal to ma. It's accelerating. But in my y direction, I have my force normal, and then I have negative mg cosine theta. It's not moving in the y, though. It's all equal. So that's all my forces, the y, are equal to 0. Okay, this is going to be kind of cool. Before we get started with anything else, let's rearrange this. So I have force normal minus mg cosine theta is equal to 0. That means my force normal, like we found in the first problem I did on inclined plane, is equal to my cosine portion of my force, okay? Now, let's deal with what's going on the x direction, because let's look for acceleration this time. So, I have mg sine theta minus my force of friction is equal to mass times acceleration, okay? Now, for my force of friction, we need to think of the equation for that. So go back in your notes. That's going to be mu, coefficient of friction, equals force normal equals mass times acceleration. Now I can plug in for force normal what I found up here. So there's a lot of math going on. So make sure you take a moment to really understand where I'm going with this. So I have mg sine theta minus mu, and I substitute that in, mg cosine theta equals m times a. So from here, I can solve for a lot of different things. Before I do anything though, I can get rid of all these m's. They all cancel. Nice, much easier problem. So now at this point, I could solve for acceleration or I could solve for mu. It really depends on the situation. So the last topic I'm going to cover today is objects that are linked together. We will be doing this in our lab that is in 2 weeks. So it's important that you get the concepts, but don't worry if you're still a little bit confused because we will be going into this more depth. Okay, so in this situation, we have two different masses, okay? And these masses, as you can see in this picture, mass 2 is larger. So we are going to assume that this object is going to accelerate downwards. Now, let's do our free body diagram just right on this. So for mass 1, we have our force of gravity, which is m1 times g. And then we have the tension that's going up. Now on the other side, we have the tension that's going up, and we also have our force of gravity, and this is m2g. Now, this is super important. Both of these objects are accelerating. Now we know the acceleration is down because m2 is heavier, but they're still going to accelerate at the same rate. Here's the kind of cool part about this. Because this is one system, we're going to have a coordinate system that actually moves with the object. So if we start on the m1 side with our standard one, as this goes around, it's going to continue. So now my positive becomes negative and vice versa. This is because this is one system. Anytime I have one system, wherever this goes, my coordinate system travels with it. Okay, so let's think about this. For m1, my force total is equal to tension minus m1g. Now this is moving, so it's equal to m1a. Now, let's write that again so it makes a little bit more sense. And we don't know our acceleration, we don't know tension, but we know both sides have tension. So let's solve for tension on this side. So tension equals m1g plus m1a. That'll give me tension equals m1, g plus a. Okay, let's go to the other side. So now for m2, we have my force net, the total force, is equal to m2g minus t. That's because I have to flip my coordinate system. It travels with the system. Okay, so this is also equal to m2a because it is moving. So now I have m2g minus t equals m2a. Now let's solve for t because t, tension, is what's connecting these two objects. So I'm going to have m2g minus m2a, and that's going to equal to t. And then I can pull out an m2, and that's going to equal t. Now let's combine this so we can solve for acceleration. And this is where the math gets really fun. Okay, so I'm going to take my two t's. So just as a reminder, I have t equals m1 g plus a. And then on my other side, I have t equals m2 g minus a. So let's set those equal to each other. So I have m1 g plus a, and that's equal to m2 g minus a. Now we're solving for a, so we need to distribute again and then put all the a's on the same side. So let's distribute. So originally I didn't have to, but I wanted to show you kind of the simplicity of a lot of the math that we're doing and how nicely it kind of comes together. Now let's put all our a's on one side and all our everything else on the other side. So I'm going to have M1G plus M1A plus M2A. I brought that over. And then let's move this guy to the other side. I'm just going to erase that. So at this point, I moved a lot of things over. Okay, so now I need to solve for A. So I'm going to pull out an A. And then I'm going to be left with M1 plus M2 equals, and I'll pull out a G2, M2 minus M1. And then let's solve for A. So I'm going to have A equals G, M2 minus M1, all over M1 plus M2. So there's a lot of derivation in this, but this is going to get my acceleration equation. So it's important to note that my gravity is still in this, and the way my masses are added and subtracted is going to depend on it. All right, so thank you for getting through this flipped lesson. I hope you took some breaks in between, went back and watched things, so on and so forth. Here's the most important part of this, and these are tips for solving these problems. First of all, make sure you actually read the problem. Don't just look at it and get scared, okay? Actually read the problem. Then you need to draw something out. What does this look like? Then you need to free body diagram all of your forces. This is super important. Then you need to choose an axis system. So if you're at an incline, we're going to tilt the axis system. Or if they're connected, the axis system is going to change with it. Then you need to determine your unknown, or what you're looking for. If you have any angles, you need to break them up into X and Y components. And then you need to break up into your X and Y table. For most problems, we're going to have to do this. Then you need to determine whether the situation is at rest or constant velocity, or is at acceleration, okay? Remember what I said, everything boils down to these two facts, whether it's at rest, sum of forces is 0, or is acceleration. Then you can solve. I also recommend that you stay organized. I can't emphasize how important it is to stay organized, label your work, and also redo it if you have to. Thank you for listening to this flipped lesson. I hope you took some good notes, and we'll be going over most of this in class.